So we can get started. I'd like to welcome you to the afternoon session. The first talk is by Professor Eli Yablonovitch from University of California, Berkeley, and Hong Kong University of Science and Technology Institute for Advanced Study. And the title of his talk is Spontaneous Emission Rate is Enhanced by an Optical Antenna.
Okay, so it's my great pleasure to be here and talk about this topic. And a lot of what I look at in this field that gets me very excited has to do with optical antennas. And optical antennas are actually quite similar to microwave antennas. And they appear everywhere, especially in your cell phone. You have this, and certainly we're becoming more of a wireless world. Now, if you imagine this type of antenna, it's a bow tie antenna. One of the things we learn is that we tend to concentrate the energy into a very, very small volume, depending upon how pointy the bow tie is. So that's a bow tie antenna. This is more of a monopole antenna. You see a sharp tip, and you can think of this as perhaps operating at audio frequencies, at low frequencies. It's still able to get fantastic resolution, and that's the scanning tunneling microscope. But it doesn't change much. If you apply optical waves, you're still concentrating the energy down to a small spot. It doesn't really matter that much what is the wavelength. What matters is how sharp is the tip. And if it's a very sharp tip, it's also a good microscope. There are so many kinds of antennas. We should not be too surprised at the strange shapes. There is kind of these types of antennas are called complementary antennas. Maybe you make an antenna out of a C, but you can also make it out of a complementary C. This would be a slot like this. And what's very useful for me is whenever I look at an antenna to anticipate where is the LC circuit, because there is an LC circuit in every antenna. In fact, when I teach this to undergraduates, I ask the undergraduates what is their personal LC frequency. Well, but they have a certain height. They have an inductance proportional to their length. Maybe they're 2 meters tall, and they have a certain inductance. And from their head to their toes, there's a certain amount of capacitance. It's the same here. So the human body is an antenna. This is also kind of an antenna. You see a capacitor, and you see that there's an inductor here. There's actually 2 inductors in parallel. And this is the reason why it doesn't much matter. If it's a C, it would be maybe just a simpler circuit like that. It's also an antenna. This is also an antenna. This is an inverse bow tie. And you could complete the circuit this way and that way. And so there's always a little LC circuit. Of course, this big loop, these are 2 inductors in parallel. This has low inductance, and this is a capacitor. So this is just something to keep in mind. Often, we invent something in optics, and they've already invented this at the radio frequency domain. So here is a very clever grating coupler with a taper. You see it's a tapered grating coupler, and the purpose is to take plane waves and convert them into surface plasmons. And well, if you look carefully at this tapered periodic structure, well, they have that. That's called a Yagi antenna. And you see it, well, you used to see it very often on suburban rooftops. Now everybody has cable television. But here is your periodic grating structure, if you like, and it has a taper, which is helpful for many applications. So there's an example of a different kind of antenna. Here is a set of antennas. I pulled this out of a presentation for the different possible antennas that are going to be used to heat up hard disks. So the hard disk industry is going to be writing, very shortly, it'll be writing magnetic materials, but it'll be writing them by raising them up to the Curie point with laser heat. And you have many different styles of antennas, but they're all somewhat related. Here, at least we know what the bow tie antenna is now. Here's a couple of them. There's a bow tie, and there's the inverse bow tie. But there are many other kinds of antennas. They're all quite respectable. Here is a type of antenna I mentioned already. The optical scanning tunneling microscope concentrates the energy, but having 2 spheres or 2 cylinders is also a very respectable type of antenna. And we heard about this from Professor Pendry, and what happens when these 2 surfaces get very, very close together. And he saw non-local corrections to the capacitance. But definitely it had the effect of concentrating the energy into a small volume. And that's one of the main features about antennas. I should mention, I think I mentioned in the question period yesterday that it was Hertz, and I don't know how he discovered antennas or how he came up with the idea, but they had very few ways of detecting radio waves, and he was the first. And so he found he could put two bodies together, and it didn't have to be spheres. It could be kind of bow tie structures like this, and different types of structures with big long arms. And then he would detect the radio waves by making a little spark here. And so that's how he came across it. So I'd like to, so I think antennas are very, very important. They're part of metal optics. You could argue that it's not a metamaterial because it's a single component as opposed to a repetitive component. But it could become repetitive if you want. Now, there are certain properties, and I should mention that the physics books, particularly Jackson, is extremely weak on this subject. And so if you, like myself, if you were trained in Jackson, it's insufficient. You have to read other books. So here's a strange property of antennas. All the different kinds, small, big, they all tend to have the same cross-section. So this is the cross-section for capturing power in an antenna. It's the square of the wavelength divided by 4 pi. And this is very universal. I could assign that to my cell phone. I could say, how much power does my cell phone capture out of a plane wave? I can just put in this cross-section and multiply it by the watts per square centimeter of the plane wave, and I can figure out how much energy is actually captured. And the nice thing about this, it's universal, so surprisingly universal. So that's kind of it. There's one little modification. If you have a highly directive antenna, the cross-section gets bigger. So this is for omnidirectional antenna. You put in 4 pi. But if it has some smaller acceptance angle, you can get a bigger cross-section. Another important concept in antennas is the concept of radiation resistance. And if in physics we were taught that accelerated charge radiates, so let's figure out the amount of radiation. So this is the amount of charge. Let's say you have n charges. This is the acceleration. Since it's sinusoidal motion, I can take the derivative, pull out omega, and then I have the number of charges times the velocity. Then I imagine it is part of a wire or a structure, and I can multiply and divide by A. So now I have the number of electrons per unit length, and the number of electrons per unit length times charge times velocity is the number of electrons that pass a certain point in the wire in 1 second. So actually, this whole thing is current. That's current gets multiplied by A squared. And finally, we end up with the power radiated by an accelerating charge or an AC current. It's amazing. Every AC wire radiates a little bit. The radiation is proportional to the current squared. We just derived that. And then there's a prefactor that looks very complicated. It has fundamental constants. It has the dimensions of the wire and so forth. And just on dimensional analysis, if this is power, the prefactor has to have units of resistance because we know power is I squared R. So that's called the radiation resistance. And it's simply the coefficient that multiplies current squared to give you the radiated power. Now, by time reversal, you can say, well, you capture a certain amount of power, and by reciprocity, you should be radiating that same amount of power. And so in this way, you can take a laser beam that you know the intensity of the laser beam. You should be able to convert that into AC current and AC voltage. So you can adopt both viewpoints. You could be a laser person. All you ever talk about is watts per square centimeter. But if you use the concept of radiation resistance, you can convert the watts per square centimeter into optical AC peak-to-peak voltage, and likewise for the current. So it's a very valuable concept. One of the universal properties of antennas is that, well, it's universal in books. Everybody has an equivalent circuit for the antenna. And I mentioned the antenna has some capacitance. You can just imagine positive charge at one end, negative charge at the other end, oscillating back and forth at the optical frequency. So there is a capacitor. It has a length. There's an inductor. Usually we use antennas where they're resonant, so the inductance and capacitance just cancel each other. But they're there. Now, in addition to that, you have the radiation resistance that we just calculated, and you have perhaps a load resistance if you put a load resistor in there, and you might have some ohmic resistance because there is dissipation in the metal wires, which we're keenly aware of. And so we could actually figure out what is the equivalent AC source in the circuit caused by the external plane wave. And that's a normal thing. That's normally done in antennas. Now, another thing we learned is we don't want the ohmic resistance to dominate the radiation resistance. And so that's very important. But what is the radiation resistance? If you go through the numbers very carefully, there's a lot of cancellation. And it ends up being related to a fundamental constant. This is called the impedance of free space. It's 377 ohms. It's very hard to do antenna calculations in CGS units. So volumes 1 and 2 of Jackson, or additions 1 and 2 of Jackson, were in CGS units. And the impedance of free space disappeared and became 4 pi over the speed of light. And then you can't tell. It looks like the reciprocal of the speed of light. But it's actually the impedance of free space. In MKS units, it's very clear. And if you believe that this is important, that's equal to the speed of light. If you believe that's an important fundamental constant, it's of equal importance to know the impedance of free space. So this is often given short shrift in physics, yet it's a fundamental constant and extraordinarily important, and it represents the highest impedance, the radiation resistance that any antenna can aspire to normally. There are ways of getting around it, but normally. This is the most important electromagnetic equation that does not appear in Jackson. Of course, there's many important equations in Jackson. This is the most important one that does not appear. And it tells you the radiation Q, the best radiation Q. That's to say, the best is, of course, the lowest radiation Q, because you want radiation. And it depends upon the cube of the size. So it's perfectly normal for me to ask the students in my class, what is your personal radiation Q? Okay, just like they have a personal LC frequency, they have a personal radiation Q. And it depends upon their size and whether they've made any special effort to change their resonant frequency. So this is a very important formula, and it's the heart of small antennas. What goes wrong with antennas? How do you know you have a bad antenna? I mentioned that the cross-section is always the same. A good or bad antenna, it's always lambda squared over 4 pi if it's isotropic. Now, so one of the things I tell the students, every piece of metal that they ever saw is an LC resonator. That includes every bent nail, every spoon, every metal chair is an LC resonator. And then I go further, therefore every LC resonator is also an antenna. But how do you know you have a bad antenna? The way it manifests itself is in bandwidth. A good antenna has a very wide bandwidth. It means it radiates extraordinarily well. A bad antenna, it still has a good cross-section, but the bandwidth is extremely narrow. So for example, in cell phones, the struggle is not to increase the cross-section. The struggle is to increase the bandwidth to the full allotted bandwidth that the cell phone is allowed to use. And so that's the struggle. So these are your bent nails. That would be a bent nail. And other things. Paper clip is down in this area, as opposed to things that are more cleverly designed, which would give you the broader bandwidth. Now, how did I learn about antennas? I learned it the hard way. I started an antenna company thinking my electromagnetic education would be enough to carry me through, and then I discovered I didn't know much about the subject. And so the company, nonetheless, we learned, and the company grew. And last year, they announced that they had shipped 500 million antennas. And to give you an idea, that's roughly 1/10 of all the adults on the planet. So, and they're carrying, I'm very proud, they're carrying our technology next to their body. The company did very well this year. They got the exclusive contract for the Samsung Galaxy 3S, which was heavily advertised during the Olympics. And so we had to learn a few things. Now, I know that I have stirred up some controversy here by questioning the metamaterial viewpoint And so let me just say about this is that there are many amazing properties that emerge from the metamaterial viewpoint. But there is an alternate viewpoint, and that's the circuit viewpoint, where you might see that this is the circuit diagram for an antenna. And if you squint, it looks a little bit like one of these elements, because indeed these elements are LC circuits. Every LC circuit is an antenna. And within circuits, there are also many amazing properties. So I'm not saying to pursue one way of looking at it or to pursue another, but we should look at it from both viewpoints, depending upon what we're doing. And maybe we should have a more unified viewpoint that does not require always to have repeating units. That would be a metamaterial, but we should also include optical circuits as part of this field. And perhaps the unified name would be metal optics, although I'll admit that's a boring name. Let me show you some more circuits. I'll show you the circuit for surface plasmons. So for surface plasmons, you can define kinetic inductance, and then the geometrical Faraday inductance is also kind of interesting. It's these formulas. Surprisingly, between these positive charges and these negative charges, maybe not surprising, there is actually a capacitance. And because there are actually currents flowing back and forth, there's actually an inductance. And you can, those are a little hard to calculate, but you can calculate them and then plug them into a circuit model with only 3 elements. And with only 3 elements, you can do a pretty good job. This is the circuit model, and this is the exact model solving Maxwell's equations. And it's pretty close. And it captures, I think, most of what's going on in surface plasmons. You could even have double-sided plasmons. I'm only showing these because they have more complicated circuits. The most general double-sided parallel plate plasmon, as far as I can see, has 10 elements, not 10, but rather 5 elements, 5 circuit elements, and they fit extremely well to the exact solutions. What about plasmonic effects? So antennas are not inherently plasmonic, but as we go to optical frequencies, the plasmonic effects emerge. And one of the most interesting effects that does not occur in the microwave region is that whereas you might have at the outer reaches, this is a bow tie antenna, the outer reaches of the antenna behave rather normally. They have a normal impedance, certainly less than the impedance of free space. But as the current gets concentrated near the tips, you pick up extra inductance. That's kinetic inductance. And that surprisingly gives you a higher impedance. So plasmonic antennas can actually achieve an impedance greater than the impedance of free space. And that's certainly one of the remarkable effects. Now, I'd like to emphasize what I think is one of the most important properties that has me excited is the possibility of increasing the rate of spontaneous emission. If I put an atom or a molecule and I surround it with an optical antenna, I believe that I should be able to increase the spontaneous emission rate by many, many orders of magnitude. And now I have here, it's not exactly a back of the envelope calculation, but it's a back of the PowerPoint calculation. It's just a little bit of a calculation anticipating what is the fastest rate of spontaneous emission. And if you have a charge oscillating in a molecule, you can actually assign a current to that. It's the charge and oscillating back and forth at a certain frequency. For the radiation resistance, I want to put in the maximum, which would be the impedance of free space. And you can go through, and if you end up normalizing the spontaneous emission rate to the optical frequency itself, you end up with the fine structure constants. This is somewhat surprising, but not too surprising. If you look at the fundamental units, h bar equals 1, c equals 1, the fine structure constant is electric charge squared. If you had a bigger electric charge, you would actually have more radiation. So it comes up in radiation problems like spontaneous emission. So in this approximation, you can still at incredibly high speed, it would be 1/137 times the optical frequency. That's a fantastically high speed spontaneous emission. And so this is making that same statement. And now there are other geometries which I'll show you that you can actually start to approach the optical frequency itself. Maybe it's possible to imagine that. So you can get really fast spontaneous emission. In fact, spontaneous emission can be faster than stimulated emission. This is, of course, completely contrary to what I was taught during my career, is that stimulated emission is always faster. And the way to think about this is that the spontaneous emission is responding to zero-point electric fields, which tend to be highly concentrated in this narrow region. And on the other hand, the spontaneous emission is indeed proportional to that 0-point energy density. However, stimulated emission is responding to a pump wave, which is a real electric field. It's not a 0-point electric field. And in all other respects, the spontaneous and stimulated emission are similar. So there's no doubt that we can produce a higher 0-point field than we could tolerate the corresponding electric field in a laser, because we would end up burning the gain medium by having such a big electric field. But a 0-point field does not burn anything. In fact, I used to be taught that it was just an imaginary concept. So it's from this idea. This involves a little bit of quantum optics, but it says that it should be possible to make spontaneous emission faster than stimulated emission by having a tremendous concentration of 0-point energy. Now, why is this technically important? Well, it has to do with optical communication. And if you try to communicate with a light-emitting diode, which you would typically do with your remote control for your television, the fastest speed of modulation, it's adequate for the television, but it's about 200 megabits per second. The fastest lasers that are useful are really only about 25 gigabits per second. So if we could just do a 200 times speed up of spontaneous emission, the LED would become faster than the fastest laser. So the question is, can we use an antenna to speed up the spontaneous emission by what seems to be a manageable factor of 200? And that's the goal which we have set. And if we do this, we'll end up with LEDs that permit communications faster than the fastest laser, and we could maybe make materials that don't fluoresce. Well, we could maybe make them fluoresce. Could be useful for biosensors, et cetera. So let me mention the material that we've used for this work. It's a rather remarkable semiconductor because it breaks all the rules for semiconductors in that you don't have to treat the surfaces. And it is this particular alloy has the rather strange property that a bare quantum well of this alloy actually does a reasonably good job radiating. You don't have to do what you normally require, which is surround it with a wider bandgap material. So I once called a naked quantum well. You could just pattern it, a little speck of that particular semiconductor, and it radiates rather well. I'll give you an example of some old data. We had this naked quantum well, and where the bulk emission would be way out here at 1.6 micron vacuum wavelength, you could have this very thin layer and observe the luminescence, and it shifted due to the of course, the normal quantum size effect. But then because it's bare, we could just put it in acid, remove a little bit of material, and as we removed material, it kept shifting toward the blue and toward the blue till we had a very, very thin layer. So this is an amazing thing you can do with a naked quantum well that you cannot do with a material that you have to treat more carefully. So we decided to use this material for our studies of, in other words, we had this little speck. We had a little speck of this material, and we basically put an antenna on either side of it. Antenna here, and we observed whether we could get radiation. Now, in these experiments, I have to be very careful because oftentimes you see an increase of emission, but it's not due to increased spontaneous emission rate. It's just due to the ability to extract light better. And there's a big issue in all LEDs. You can definitely make a big improvement from extracting light. We don't want that. We want it to be an actual spontaneous emission enhancement. And sometimes you put metallic structures on the back of an LED, and the main purpose is to randomize the light directions to make it easier to extract. That's not what we aim to do. Now, in putting this little quantum dot of indium gallium arsenide on, there are ways of making things even faster. For example, if you build a little resonant cavity around the light emitter, then you can say, that resonant cavity, that's like enhancement by the Purcell effect. So indeed it is, and this type of LC circuit is often used in antennas and greatly helps the spontaneous emission, basically by improving the impedance matching. However, it's nothing as glamorous as the Purcell effect. In fact, engineers simply call this a matching network. but it just shows you have to be a little bit suspicious of the Purcell effect, because imagine going up to an antenna engineer and asking them, oh, are you using the Purcell effect? And they'll say, well, you're crazy. You know, I'm just an engineer. Okay, but indeed, it's very similar. So I show this as an example of the antenna we use. Actually, did build a little cavity in here. This was the gold antenna, and then it jumped over the little speck of indium gallium arsenide. And you can visualize that there was an effective capacitor here, and there's an inductor. So this is a little second LC resonator in there. So these are the structures that I'm going to show you. And I'm going to show you the light emission where you're emitting in that direction, where you don't expect the antenna to help, versus emitting in that direction where you do expect the antenna to help. And always, just to keep things clear, we always pump in this direction because we don't want the pump to get confused with the antenna direction. And so this is an example of what you see in the different polarization directions. We start with indium gallium arsenide ridges. They're very long. Of course, the only part that gets enhanced is that little part. And so it was very important that to start reducing, eliminating all of this material that isn't contributing. And so when we eliminate it like this, then, of course, the desired spontaneous emission grows. And then it grows even further when we have this little tiny ridge. And most of that ridge gets enhanced. So we have this little ridge. This is the part where we expect the enhancement. The two things on either side probably don't get much enhancement. And we compared the spontaneous emission with the antenna versus without the antenna, keeping all other things equal. And so this is an example of what you get. In the wrong polarization, it doesn't matter whether you have an antenna. However, if you're polarized, looking for luminescence parallel to the antenna, you get a very substantial enhancement. Of course, the antenna helps a huge amount versus not having the antenna. So let me show you our best results. This is the emission parallel to the antenna. So emission in this direction compared to having no antenna. And we have observed 35 times spontaneous emission enhancement. So this is quite good. I should mention that I believe this is the highest that's ever been seen in a semiconductor, although with molecules and antennas, people have seen a little bit higher. The claim is up to 60 or 70 times spontaneous emission enhancement. So this is very gratifying. However, it doesn't get up to 200 that we're hoping for. So what are some of the limitations? You've got to bring the arms of the antenna as close as possible to the quantum dot. And to the extent that the arms are not very close, there's a penalty. And this is how close the arms are divided by what is the electric dipole moment of the transition. So we suffer a penalty, and we hope to bring the arms closer together. It means that these two parts have to get even narrower and closer together. And we should increase the enhancement that way. Here's another approach that we're taking toward increasing the enhancement, is to have a layer that's defined vertically. So the vertical distance, the spacing between the two arms of the antenna, is controlled by things that we can control very well, not E-beam lithography, but rather simply the layer thickness, which we can control very well, and we're trying to do that. Now, people often ask, oh, well, yeah, you have a increased spontaneous emission. What about the efficiency? So this is something that people don't necessarily appreciate that well, is that the radiation from antennas is very, very strong. In fact, any good antenna has a radiation Q of the order of 1. That means in one optical cycle, almost all the energy goes away. Now, of course, that has to fight with the ohmic losses. Now, in plasmonics, we often have an ohmic loss around 10. And if that's the case, you'll see that they just look at the Q of 1 versus the Q of 10, and you end up with an efficiency of the order of 90%. So efficiency is very important. There's no point having a fast communications LED unless it's also efficient. So this is a general requirement then for efficiency, is that the ohmic losses have to be less than the radiation resistance. Radiation resistance tends to be around 50 ohms at best, but it could be a little higher. So what limits us then is indeed series resistance associated with the antenna and the little quantum dot emitter. And in this regard, electron collisions do make a big difference, and there is this important non-local effect, sometimes called the anomalous skin effect. And the way to think about this is that, yes, the oscillating charge in the molecule, that creates currents in the antenna. That's all well and good, but the currents tend to be concentrated near the tip. And the very concentration itself forces the current into a smaller area, so you end up with bigger series resistance. Now, in electricity, this is called contact resistance. When you're trying to conduct from a very small area, you have extra resistance just because the current is crowded. But in addition to that resistance, that is just a concentration of current, you also have extra resistance because down here, you actually have more surface collisions as well, and that's the non-local effect. And so it competes a little bit with this high impedance. The high impedance will ameliorate it to some extent. And so this is what we're struggling with, is what is the actual expected resistance when we have this tremendous concentration of current, of course, on both sides. And that we don't have very good numbers for. I can make estimates, but it's ultimately going to tell me how fast I can make the spontaneous emission. We're up to 35 times enhancement. If I can get 200 times enhancement, I beat the fastest laser. Can I even get to 2,000 times enhancement? Everything hinges on this series resistance. And the series resistance, surprisingly, nobody has done a really good job of calculating it. It's a hard calculation. It involves non-local resistance as well as the normal current crowding that occurs near a sharp tip. Now, to give you an idea of some of the issues that come about, everyone knows that if the electron collides with a rough surface, it'll lose its momentum. And that's definitely bad. That's a surface collision. What people sometimes overlook is an electron merely leaving the skin depth takes the optical AC momentum with it. And that also acts as a kind of loss mechanism. And so both of these contribute to the anomalous skin effect. And surprisingly, the Fermi velocity of the electrons enters the relaxation time. So it has some interesting physics in it. So let me conclude then, is that it seems like these particular quantum dots make it really easy to do the work because they're just little islands. We have demonstrated so far 35 times enhancement. I should say we've made steady progress. Last spring it was 25 times. So we've definitely improved things. But we will, as we make that spacing narrower, we'll get more enhancement. The big question, can we really beat the laser? And it seems like, although we've observed 35 times, part of the indium gallium arsenide was a rod. The ends of the rod were not really experiencing the enhancement. So maybe we had 100 times enhancement. And so we hope to go further. But the anomalous skin effect will eventually limit us. And the question is, where will that roadblock occur? Will that allow us to get to 2,000 times enhancement? And if so, then we would have a phenomenal modulation speed. So this is of great interest for internal communication within chips. It depends very much upon our ability to increase the spontaneous emission rate. If we're successful, we will have nano LEDs that are faster than the fastest laser. It'll be helpful for fluorescence, or for assisting fluorescence, maybe for biosensors, and so forth. So there's a reason to do it, but I just want to finish up with this viewpoint, is that there's great value in the metamaterial viewpoint, where you have a repeating structure that goes many, many times. But there's also great value in looking at the individual structures themselves that also have a lot of beautiful physics and many great opportunities for new science and technology. Thank you.
Actually, this enhancement of spontaneous emission on the order of several hundred is certainly not out of reach. In 2008, we experimentally saw 100 enhancement of spontaneous emission from dye molecules sitting next to bow tie antennas. And
Yeah,
I'm absolutely sure it could be accomplished. It's not
Yeah.
a big deal.
Let me just say, in the dye molecules, I need to look at your paper. The highest number I've seen for dye molecules is 60 times or 70 times. But I'll be happy to take a closer look to see if it stands up. Yeah.
Well, if I look at a single molecule, then certainly I have spontaneous emission. But in principle, if you have a laser or an emitter, then the spontaneous emission will back action on the active material itself. So you will have something like amplified spontaneous emission.
Right.
Do you anticipate that this will even more change the speed or velocity?
Yeah, so the argument I've made is that we could amplify the just like you're describing, you amplify the stimulated emission. We have overlooked the possibility to amplify the spontaneous emission by providing an antenna. The way to think about this is that a molecule, in order to spontaneously emit light, it has to store the energy and then has to radiate the energy. But molecules are too small to do a good job radiating the energy. A good radiator should be half a wavelength. That's like a typical antenna size. But the molecules are typically 1,000 times too small to act as good antennas. And this is the main reason why the spontaneous emission is regarded as so weak. And then if you look into antenna theory, you say, oh, maybe you have a penalty of 1,000. Actually, look into antenna theory, it's 1,000 cubed. So there's a tremendous loss of spontaneous emission speed associated with the fact that atoms are 1,000 times smaller than wavelengths. And so that's what we're trying to overcome, is to provide the atom or the quantum dot with proper sized antenna.
Any other questions? Oh, yes. Wolf.
So if you make the spontaneous emission really fast, then of course it means in the spectrum you're broadening the line width incredibly.
Yes.
But now can it happen that the lines then overlap, so you can't really separate energy levels anymore, and that could ruin the operation of your device?
Well, actually, this kind of broadening is actually desirable because that is representative of the bit rate. So we want exactly that type of broadening. But don't worry about having sharp spectral features that are adjacent to other sharp spectral features. The semiconductors typically, they just have this one major feature, which is the bandage emission. And so we're expecting to have a spectral width corresponding to the bandage emission. It's quite broad, but the breadth is consistent with the modulation speed we want to achieve.
Okay.
I should mention one more thing, is we do need theoretical help to estimate what is the maximum enhancement we could have. And I think it has to do with this with these non-local ohmic losses. And if you imagine, I just gave you a calculation for what to expect. I said it goes according to simple theory 1,000 cubed. There'll be 9 orders of magnitude of enhancement. I don't really believe we're going to get 9 orders of magnitude of enhancement. So the actual amount of enhancement that we should expect, I think that we need some help.
Very good. With that note, let's thank Eli one more time. Thanks very much.
Okay.
So I also want to thank the organizers to invite me here. I spent some time here many years ago, and it's good to see some old friends and the beautiful campus here. This talk is about a fairly simple device. All it is 2 parallel plates and 2 slits. It could also be 2 little holes. And so it's fairly simple. You can solve this problem analytically in the limit when the slit width is very small compared with the wavelength. And assuming that you have a perfect metal here, but I will also show you results of simulations with real metals. And if you look at the transmission here, this is transmission as a function of frequency. You find a very sharp resonance here, where at this frequency, the transmission is 100%. Provided, of course, you focus the incoming light down to the diffraction limit. So you focus here, I'll tell you more about it. And the reason why is this possible is because this structure has a localized electromagnetic resonance there. And for the people in condensed matter, this looks like an exciton. It's below the continuum. It's localized. And when you when you match the frequency of this resonance, which is below the cutoff, the waveguide cutoff, you get 100% transmission. It's a localized electromagnetic state. It's a singular perturbation. If you don't have the slits, there is no localized state. And no matter how small the slit width is, you get the localized state. I will tell you more about it, but you see a kink here? There's a little kink here. This is where the cutoff is, right at the kink. So let me then start the story by telling something that many people here know very well, is the question of transmission of a wave through a very small aperture. So this is the problem that Hans Bethe, when he was very, very young, I thought this was something he worked during the Manhattan Project, but somebody corrected me that apparently wasn't exactly true. So I don't know exactly why Hans Bethe worked on this problem. And what he found is that the ratio between transmitted power, this is a way to tell you about how much of a wave gets transmitted through a hole. What you do is you get the total transmitted power divided by the power incident upon the hole. All right? So he found that it was the ratio between L is the size of the hole divided by lambda to the 4th power. It's a very small number. But let me add a little more to this. Suppose you have a diffraction limited spot. In other words, suppose that all the light is, the best you can do is to focus the light to a region of radius on the order of lambda. That's the best you can do using conventional optics, not with a negative index lab, but conventional optics will do this. So the power incident upon the hole is the incident power divided by the length of the hole divided by lambda squared. This is what gets through the hole. So if I multiply this times the result of beta, you find that the power transmitted, the best you can do, is the incident power times this ratio to the 6th power, which is very, very small. And this being as small as it is the reason why back more than 10 years ago, the paper by Resin and collaborators made such an impact, because what they saw was that certain structures, metallic structures, could actually show significantly more transmission than what you would have expected for a small hole. I have here some of the papers. People are sitting here in the audience. And this is something that I think is fair to say. This is what is known as extraordinary optical transmission. And it's fair to say that there's a fairly good understanding of what is causing this. And you get this sort of transmission, very large transmission compared to what you would have expected due to coupling with certain resonances. The resonances could be surface plasmons, waveguide mode, Fabry-Perot resonance, et cetera, et cetera. This is a structure that, for some reason, has received a lot of attention recently in the literature. This is what is, some people call it the funneling problem, how light goes through very narrow slits in here. And I'll be saying a few things about it. So, so you may ask, well, since we've been working for so many years, working with a razor hole, why would anybody care about one set of holes? So this transparency is to kind of motivate the reason why one would worry about a single hole. This is a fairly old problem. What I showed before, this structure that is associated with funneling, is something that experimentalists have used for many, many years to polarize infrared radiation. So you make these groups in a metal, and if you polarize like this or like that, you get very different reflection and transmission. It was used. People have understood this for a while. This paper is a more modern version of our understanding where we start talking about permittivity and permeability. If you look at the old work, the word permeability is not even mentioned there. And here's the structure again. And so if you have a perfect metal, this structure has, of course, is anisotropic. And you can view this as a waveguide. So if the electric field is polarized like this, you can just go through. And if in addition to that, you have a Fabry-Perot resonance, then you get extraordinary transmission. However, and this again is something that has been done because the single slit problem can also be solved analytically. You find something that I don't know if people in the audience have already seen this, but it's the following. If this length here, h, the height of this group is exactly lambda over 2, which is you are in the Fabry-Perot resonance, then you get 100% transmission for an array of groups. However, for one group, you get 0 when the thickness goes to, when the slit width goes to 0. So the two problems are not the same. And I will tell you a little more about the single slit problem. So here is the result. This is an analytical result. When A, which is the slit width, goes to 0, the transmission through a single hole goes to 0. Whereas the array is 100%. All right, so can single holes do better than the better result? And the answer is yes. If you couple the holes to resonances, much in the same way that extraordinary transmission happens, it's also the case with holes. And this is something that if you go back in the EE literature, you're going to find a couple of papers, not too many, that show that, paper by Harrington, if you couple a hole to an LC resonator, you can get 100% transmission. This is another paper where you couple the hole to a cavity, and you can get also, if you put one hole there, this is not exactly the case, but if you put one there and one there, you get 100% transmission. And the mathematics and the physics of this is closely related to resonant tunneling. In case somebody is thinking about that, yes, it is. But it's not exactly the same. It's not exactly the same. So the answer is yes. If you have resonances, you can actually have, in the perfect ideal case, 100% transmission. And let me just say that in 3 dimensions, 100% transmission means that this normalized transmission is lambda over the size squared. And I didn't mention this before, but there is a close relationship between this device and the antennas you listened to in the previous talk, in that this device, as a resonant antenna, captures what is in the region of lambda and puts it in one spot. Okay? That's what it is. Whether this is a good antenna or a bad antenna, as we heard before, depends on the Q. And here you can vary the Q quite easily by changing the slit width. So if you have a very small slit width, I'll show you data from simulations in a minute, you can get Qs close to 1 million. But if you start to increase, say, lambda over 10, you can get 1,000. I'll show you data even in the visible region, how it works. All right, so let me show you a quick physicist description of how a hole can give you 100% transmission if it's coupled to a resonance. So this is the hole coupled to, you see, you guys use LC resonators, I use springs. Okay? Just to be different. By the way, this, much of what I've been telling you and about to tell you has been published in a Physical Review X. It's a new journal of the American Physical Society. And we are very fortunate that one of the editors is here. Right? Okay, so here is the very quick version why a resonated hole gives you 100% transmission. So if you remember from Jackson, when you have a little hole in a waveguide, what the hole does, it behaves like a magnetic dipole or an electric dipole, right? So when the magnetic field is parallel to the surface of the hole, you get an induced magnetic dipole that I am going to put the resonance. So this is, instead of just taking the, look, at zero frequency, if I have zero frequency, the magnetic dipole is what it should be, is the cube of the length of the hole times the magnetic field. And all I did was to add the resonance in there. And if you add the resonance, and you are careful, and you assume that the only losses that matter are radiative losses, you can calculate that constant there by equating the power that the magnetic field gives to the hole to the radiated power. And if you do this, you find this expression. Here it goes like the cube. That's what you get. So if you put this value of tau back in there, you get 100% transmission or very close to that. That's how it works. Okay, very, very, very simple. All I did was to add a resonance. The question is experimentally how to actually make that resonance is a different question. But at least if you have a resonance, this is what you get. All right. So let me move on now from 3 dimensions to 2 dimensions. It just happens that the 2-dimensional case can be solved analytically. The 3-dimensional case cannot, as happens many times. So let me just mention that in 3 dimensions, perfect transmission means that this normalized transmission is lambda over L square. In 2 dimensions, it's lambda over L. Okay? So back to the device I told you. So this problem is one that, similar to the funneling problem, people studied a lot in the p polarization. That is when the electric field is here. So I am working on this in the other polarization, in the S polarization, when the electric field is perpendicular to the screen. Okay? It is in that polarization. Well, both cases can be solved analytically. And as a matter of fact, in the electric engineering literature, the p polarization, there are 1 or 2 papers on that. Leviathan solved that paper for p polarization. So this resonance I told you about does not exist for p polarization. It exists only in S polarization. So this is, again, the transmission in the logarithmic scale, and this is a linear scale, and this is the state in there. And as I said before, it's a localized state that is something that is a singular perturbation, as I said before. If you have hole, you have it. If you don't, it goes away. So this is another way to look at the same problem. These are the pair of slits. This is my exciton, my localized electromagnetic state. So very close to the Fabry-Perot resonances, you get this. And you see the difference between the 2 polarizations. This is the yellow one is the case that has been studied the most. And there is not a real resonance. There is a cusp in the transmission. And the transmission is pretty much flat. However, in the other polarization, you get this very, very sharp resonance. And right here is actually an interference effect. I can even call it a fan of resonance, but I will not. It's not. It's not a fan. But it's an interference effect between a background like this and the sharp peak. That's what gives you a cusp. All right, so this is a picture. I mean, you can calculate. This is all analytical, and this is the localized state here. And you get 100% transmission, which means that most of the intensity is inside the waveguide in that state. On the other hand, this is the localized state. I emphasize the electric field is polarized along Y. It's along the slit. Okay. And this is the case when the frequency matches the frequency of the cutoff, the beginning of the continuum. And you don't get, the transmission is very small. So this acts, in essence, like a mirrorless cavity, right? Because I have eliminated the lateral walls here. I don't need those walls because the state is localized. Okay? So that's an advantage. It helps you avoid losses by not having those walls. The phenomenon is fairly robust. I mean, it's easy in a computer to shift these two slits, and you still get the resonance. The localized state, you can move the two slits within a wavelength, and the localized state is still there. And in 3 dimensions, you can do the same thing. It's still there. Okay, another picture, and this is the cutoff mode. You see, when you the frequency is equal to the cutoff mode radiation, the wave go to the sides. That's why the transmission is significantly less. This is the circuit equivalent of vacuum, and this is the circuit equivalent of the waveguide. Eli, for you. These are the holes, right there. You're supposed to laugh, but okay. Anyhow, this is how, as the frequency varies, you see that the state goes, and when you hit the cutoff, it's completely extended. It's just a cartoon. Let me say something about resonant funneling, particularly because there are so many papers that came out recently. These are a few there. The story goes again back to people like Harrington, who looked at this problem a long time ago, and as it happens many times, we look at it again and again. So here it is, and this is again the kind of structure that people in extraordinary optical transmission have looked very carefully. These are some recent papers. This is an exact solution in P polarization. Takakura. And this is some very recent paper appeared last year. So what I want to do is to compare 3 cases and tell you something that I think is kind of intriguing. So this is a slit carved in a piece of thick metal. This is a single slit, and this is the problem I've been talking about. The result for these 3 geometries when you are in resonance is identical. Identical. So what we call resonant funneling, that is when the height here of the slit is lambda over 2, gives these results for Ex and Ey. In other words, all this in resonance behaves like a single slit. You haven't gained very much. It's identical to a single slit. And same here, in the bulk resonance, the same as a single slit. So you only get extraordinary transmission when you hit it at the localized state. Okay? So, and like I said before, the actual transmission, this is the normalized transmission, but the actual transmission when delta goes to 0 goes to 0. Whereas here, the actual transmission when delta goes to 0 is 100%. It's singular perturbation. Okay, does it work with real metals? Okay, so we did numerical studies using a waveguide instead of, but remember, we are focusing the waveguide down to the wavelength of the light. The trick here is to use a bevel. If you don't use a bevel, it doesn't work quite well. So bevels do 2 things. The transmission is larger, the Q gets smaller, and the binding energy, that is the distance between the binding frequency, the distance between the position of the resonance and the cutoff increases. I'll show you numerical data. So a lot of things happen. This is how things change with the wall thickness. So this is, for example, the frequency of the resonance as a function of thickness for different values of the bevel. So 30 degrees, 45 degrees, 90 degrees is no bevel. Okay, and you see how things vary here. This is the frequency. This is the transmission. You see 90 degree, when it gets to be thicker, the transmission dies very quickly. But if you put the bevel, you get a lot of transmission. And like I said before, you can put roughness, you can move the holes a little, and the resonance, it stays there. It's very, very robust. So here's data, copper, 10 gigahertz. So what we do here, this is for a bevel of 45 degrees and a slit width of λ/10. As the walls get thicker and thicker, the resonance moves to lower and lower frequencies. The cutoff is always the same, right there. The cutoff is the cutoff of the waveguide. That doesn't change. And the Qs are on the order of λ/delta to the 6th power. In 2 dimensions, the Qs have a much larger, higher power than in 3 dimensions, significantly larger. So in principle, if anybody cares about that, you could get Qs of 10 to the 12. More likely, they are going to be 10 to the 8. Okay? So this is for copper and is simulation. We are doing the experiments right now. And this is visible. So in the visible, also at microwave frequencies, you get more than one peak. So because every continuum that starts in the waveguide has an associated localized mode, as you probably expect it to be. So this is throughout the visible, 400 nanometers, 4,000 angstroms all the way into the near infrared. And these are 2 continuum onsets. And you can play all kind of games. You can change the bevel. Things change. There are many parameters that you can use and vary. Peaks get sharper, broader, all kind of things. And what do I have there? The wavelength as a function of phase separation of the resonance. But this is more or less what you expect. Then you get transmissions and quality factors. Typically, we get quality factors here for silver using a bevel of 30 degrees. Somewhere between 500 and 1,000. And there is still room to play a little, but I don't think they're going to get significantly better in the visible. And the transmission varies between 50% and 10%, which is all right. I mean, if you want to use this as a spectrometer, they are as good or better than diffraction gratings. Diffraction gratings are not very efficient unless they are placed. So what can you do with this? One thing that you can imagine doing is to build a spectrometer that has the size of a wavelength. That's all you need. It's going to be fairly small. And in the visible, it's going to be really small. And the way this operates as a spectrometer is you vary the distance between the plates. That's all it is. Can also be used as an interference filter. So this is almost like extraordinary transmission, but now I want to put the holes separated far enough so that each resonance doesn't talk to the next one. Okay? So if they are something on the order of 2 or 3 lambda apart, they don't talk to each other. And it will be an imaging spectrometer. Okay? Because you get a nice image, and you vary the place, and you get all the colors. So other applications, well, this is already mentioned. Also, you can use it to monitor liquids, for example. They go through there, change the frequency. So anyhow, I'm done. So let me conclude. So what I discussed very briefly was transmission through subwavelength apertures. And told you something that has been known for quite some time, that resonated apertures give, ideal resonated apertures give perfect transmission. And I told you something that somebody must have seen that, but I have not been able to find a reference about this localized electromagnetic mode. So if anybody knows of this, please let me know. I did an honest job trying to find out, and I didn't find anything about this. This is, I think, an intriguing result, because particular people have discussed funneling extensively, the notion that there is something really important. And at the end of the story, they are as good as a slit, non-resonated slit. That's all they are. So remove the funneling, remove the resonance, put a slit. It works the same way. And also to place in P-polarize and show you data in real metals and discuss some applications. Thanks.
Javier?
Okay, good. Thank you. So my question is, let's see, you are saying that you don't have these localized electromagnetic states. For S-polarization, the whole system is exactly equal to the Schrodinger equation. So it reduces to the Schrodinger equation. So maybe you have electronic.
But not, it's true, but not exactly, right? Schrodinger equation and it's solving Schrodinger equation at zero energy, right? So in principle, you may or may not have a solution.
I think it's the same, formally the same equation.
Okay, let's go with the
So
details.
basically, just the scalar wave equation, which basically Dirichlet boundary conditions. Now, what I wanted to point out is that if you move to an equivalent system, which is also scalar, in a sense that is with Newman boundary conditions, then in that case, there is not such a thing as extraordinary transmission.
Correct.
There is always a massive amount of transmission. Yeah. But then my question is, you have studied this case of TE polarization with the slit, and then what happens in the hole, like with circular symmetry? Is it the same?
We also see a localized thing. Yeah, but.
And what's the scaling then in that case of the transmission? Like in the
if you hit at the resonance, you get 100% in a perfect metal.
But I mean, this 100% in the case of the slit is the wavelength divided by the.
No, 100% means always the same, right? If I focus the line down to the diffraction limit, how much does it go through? So nothing gets reflected, and you get 100% transmission. Yeah.
Thank you.
Yeah. Any other questions? Yes, Sebastian.
Yes, in fact, applied mathematicians, they know these kinds of modes.
Okay.
In fact, whenever you have a strip with Neumann or Dirichlet, and you have a little change, this could be a topographical change or just adding a defect as you did, you have what they call a cutoff trap mode. Okay. And it's exactly the shape of your mode. Okay. I can give you some reference on this.
Please. Okay, I didn't check the applied mathematics.
Roberto, I think the idea of coupling a resonator to a small aperture probably goes back to Helmholtz.
Could be. I didn't go that far.
The Helmholtz resonator is a very nice paradigm.
Yes, yes, of course. Of course.
Thank you. Any other questions? Yes, Eli.
Suppose you had a metal film with no holes, but just with some surface texturing on either side. Do you think there would be any transmission?
Well, but then it's not. It's a different problem. It's surface plasmons, and things like that. And the answer is, people in extraordinary optical transmission have studied that. The answer is, you can.
Yeah. So that would be, if you ratio it to the area, that would be infinite enhanced transmission because there would be zero hole area.
Yes. This is super extraordinary transmission.
Thank you. Any other questions? I have a question, Roberto. You showed when you go actually to the higher order modes of the waveguide, you increase the frequency, you go higher order mode. If you go to the next mode cutoff, the first mode can propagate. So how come you still get good transmission?
Good question. This is something that we got last week, so
we can talk about it.
We can talk about it. Okay. This is just comes out of. There is more to the story because I don't understand, for example, why this mode is significantly narrower than this mode. So there are some selection rules going on in there that I don't fully understand. Now, I must say something I didn't say is that the bevel changes the nature of the localized mode a lot.
Sure.
So,
yeah. But the mode is basically cutoff of the waveguide.
Correct.
That's right.
Correct.
Okay. Very good. Let's thank Roberto one more time. Thank you.